Okay, we've got three buoyancy items here. We're going to find the mass, or we're going to find the water displaced, the amount of water displaced in three different situations. One, an object that sinks, it's this mass in water. An object that floats in water, it's a little clay boat. And an object that floats in water, but we will hold underwater to see what its force is. We're going to measure buoyancy in a couple different ways here, and hopefully we can kind of, with this multiple item approach here, kind of get a better grasp on what buoyancy is about. Okay, so the first thing we're going to do is find the mass of this object. So this is the object that will sink. Let's assume that string to be a massless string. We'll put the object up on top. And we're going to add masses up here in order to determine what the weight is. So we're going to start with 500 grams, and then 600, and then 700, and then 800. This is 900, and here is 1,000. That'll make it 1,000. And you can see that that's going to be too much. If I put that on there, that's too much. So it's not 1,000. So I'm going to drop down to a 50-gram weight, and 50 is too much. So I'm going to drop down to a 20-gram weight, and another 20-gram weight. And that's too much. So I'll go to a 10-gram weight. It's just about right. We're going to call it good. I didn't have to use this slider. This slider would have given me 1/10 of a gram increments, even 100th of a gram with proper estimation. So we've got a 500, 6, 7, 8, 930. 930 grams. Jot that down. All right, so we'll leave those masses on here. I just want to show you something. If I now transfer the weight below, there's a hook below designed for this. And now if I just let it sit here, it is still balanced. I'm going to take that 10 off and slide this across to balance it. It is off by just a little tiny bit here, so I'm going to go ahead and find the difference. So we are, this is 929, excuse me while I read this final volume, 929.60 grams, 929.60 grams. All right, so now we're going to, water provides an upward force, a buoyant force. So does air, but air, it's fairly small. We don't really feel it, but you feel it in the water. And we're going to get a sense of what that is using the overflow cam. So we're going to I've checked this out ahead of time. I need this to sit up on this little ledge. Let me go ahead and get this out of the way for a moment. And I'm going to pour water in this until it overflows into this beaker. This is just going to be my waste beaker. All right, so we want this water to overflow and then just stop dripping, so that anything that we put into the water will cause water to be displaced. It's called volume by water displacement. Cause water to be displaced through this hole into a beaker that we can capture it. And so in this case, I'm going to capture it into another beaker. I'll just keep that there for later use. And so I'm going to take the object that we're trying to find the buoyant force for, and I'm going to slowly lower this into the water. We don't want it overflowing the edge. We just want the water going into the beaker. Notice that the weight now up here is greater than the weight of the object. That's because the water is helping to lift this up. And so we have to take some weight off of this side. First of all, this hasn't completely submerged, so I'm not going to remove the beaker just yet. I'm going to take off a couple 100 grams. And slide that back to 0. So we're at 700 grams right now. This will allow it to go all the way down. It's now resting on the bottom, and we need it to come off of the bottom right there. So it's got to lift up a little bit. We have, however, collected the volume that we want to collect. So I'm going to slide this beaker off to the side here just in case a little bit slops out. Just in the jostling and the weighing of it, we could get a little sloshing out, and I wanted to get an accurate volume. So we're at 700. I'm going to try 800. 800 is too much. So I'm going to go to the 50. 750 is good. Here's a 20. So that's good. Here's a 40. That's a little bit too much. So I'm going to go with the 10. And now I'm going to go with the slider. Okay, so we're balanced. Let's add this up. This is 500, 600, and 750. And that's a 20, so that's 770, and that's a 10, so that's 780. And then this is going to add on top of that. So that's a 9.70, so it's 789.70. 789.70. Compare that to our original weight, and we have the amount of weight that is apparently lost, and that apparent loss of weight is called the buoyant force. And so the water is lifting with a certain amount of force. I'll do the math later because I don't remember all the numbers right now. So we'll take a look at that later. Now we have one other thing to do, and that's related to Archimedes' principle. And Archimedes' principle says that the mass of the water displaced, this is the water displaced right here, that the mass of the water displaced is equal to the buoyant force. Well, the apparent buoyant force is what we lost in weight right here. Let's see what the mass of our water is here. So I've got a scale over here, but it may not go to that capacity. So what we can do with water is, because it has a density of 1 gram per milliliter, is we can just measure the volume. So let's do that. So we can get an estimate from the beaker, right? If I look at the beaker, I can see that that's about just under 150 milliliters. But beakers are good for estimating volumes. They're not good for a nice precise measurement. So let's do a nice precise measurement. So I'm going to pour into the grad cylinder here. I know it's over 100, so I'm going to start with 100 mil grad. All right, so we've got 100 and 42. We're going to call it 142.0 milliliters of water displaced. And for water, the density is 1 gram per milliliter, so it's 142 grams that has been displaced.